Hello, students. Welcome to a screencast with Mr. Swan. I'm a big fan of doing these in one take, so if I make a mistake, I'm sorry, but I'll at least let you know. One day I'll learn how to edit these videos, but that day is not today. So I figured I'd give you a picture of the day, and today is social distancing. I saw this graphic in the Washington Post, and I thought I would bring it on into the classroom virtually. All right. So social distancing, similar to the word social media, it sounds like it's a new idea, but has actually been around for about 100 years. The event where it showed the most success was back in 1918. There was another virus going right around. It was called, or nicknamed sometimes the Spanish flu, or H1N1. One of the reasons why is that over 80% of Spain got it, and it was pretty bad. The world population at that time was about 1.8 billion people, and about 1/3 of them were affected with the virus. That's about 500 million. From that, about 50 million people died. So the mortality rate of the Spanish flu is way more infamous than most of the other flus that happened in the preceding years. It's way higher than our current corona pandemic. So what happened is that this was going right around in Philadelphia. There was worry that it was starting to kind of come over to America. It eventually went over into like the Navy shipyard, where a whole bunch of sailors eventually got sick. That day or the next day or so, it was decided that they would still continue to do their the Liberty Loan Parade, which was scheduled for about a week later or so. So they still had it, but that also then made about 200,000 people gather together, which then caused that sickness to spread very, very quickly, all the way throughout Philadelphia. In about 6 weeks, 12,000 people had died. St. Louis, though, learning that similar lesson, decided to pretty much cancel everything. They banned people from going to their restaurants, similar to what we have done now, and a whole bunch of other places. And their death toll ended up being about 700. So the little graphic I have here on the right kind of shows like what they talk about. If you ever heard of the phrase, maybe online right now, called flattening the curve, is that this is the spike up here for Philadelphia shows that a lot of people eventually got sick and died very, very quickly. And then here for St. Louis, it goes on for much longer, but the rates are much, much, much lower. And the idea is that we can actually handle something like the St. Louis rates, where for most of the Philadelphia, our systems and hospitals could not handle it. So that is why we're told not to come to school or go to restaurants, or they have closed the movie theaters, is to try to keep that as low as possible. A little bit of a negative side effect is that it can extend this. So I know our school is closed until April 1st. It's probably expected to go longer than that. So a nice little simulator I found about this. There's one up here. I'll turn that on for you. And it talks about no countermeasures versus extensive distancing. And the idea is that you can actually see these curves actually happen in real time based on just pure statistics, which is really math and really everyone's favorite thing. So the diagram right here on the left shows a whole bunch of people kind of getting sick, and eventually that's what this little the brown outline right here is. And then over here it shows like the long kind of flattening out of that curve. If you would like to read about this a little bit more, that would be in this article. I have a little link to it, which is why outbreaks like coronavirus spread exponentially and how to flatten the curve. And it kind of goes on. The graphs are way better. The one I was actually able to make a GIF for and put for you in your class, into that slideshow. But it has a whole bunch and kind of talks about like how people travel and how would it work if you start quarantining the sick. Like how much social distancing would work. And the more you have, in theory, the flatter the curve actually goes, which then helps people over the long term. So this is over in the Washington Post. I believe this article is a free article, so you can take a look at it. I'll probably put this slide on Google Classroom, and maybe the rest of the and continuing on pictures of the day. So you can take a look at it and click on it at your leisure. So notes today, for some people, I did do a little bit more with the notes than others. So I figured I'd just go and start from weather fronts on, and I'll just finish them right up. So if you feel like you're good for a section, just skip ahead. I have a lab which I'm going to put up for you guys to work on, and I'll show you what that is. And then this is also a pretty good time to mention, if you have any past work, like any green covered labs, make sure to finish them. Don't let them hang around too much, because we'll do some stuff a little bit more with the Unit 8, the atmosphere, this week-ish. And then that's kind of it. We were just about done with it right before they closed school. And then I'll move over to Unit 9, which is mostly about climate. And so let's go get started. So these are some past notes maybe for some people. But a little review never hurt anybody. So weather fronts. A front is a boundary between air masses. So air masses are those ginormous moving bodies of air. They are thousands of miles long. They have different characteristics of temperature. So some are considered either warm or cold, or that they are wet or dry. As they move on, they sometimes will hit each other. And so when they do that, when they meet, that's what they call a front. It's kind of like the front of, like the front line of maybe like two armies kind of clashing, or just the beginning kind of front part of the air mass. And there's 4 types. The first 2 are by far the most important, which is cold fronts and warm fronts. And the last 2 are, while important, are not usually as important as those 2. So a cold front is a boundary where cold air is pushing back some warm air. It does it with a really good amount of force. This is, in theory, thousands of... let me try that laser point. Works pretty good, right? So this is, like, in theory, like thousands of miles between these 2 points. It's supposed to be many, many miles tall. And the outline of the cold air mass, as it kind of moves across the ground, does so, to me, it looks kind of like a bullet train. And it just barrels across the ground and eventually hits warm air, and it knocks it up. And when you take warm air and you knock it up higher in the sky, it cools due to adiabatic expansion. It eventually cools to such a point that it hits the dew point, which is the temperature at which net condensation is more than net evaporation. So you're going to have a lot of condensation happening in the air on condensation nuclei, and then you will form a cloud. And you will eventually form a whole bunch of clouds in this case, and a whole bunch of precipitation. And chances are probably like a thunderstorm or really heavy rainstorm. So usually cold fronts are the bad storms. Because as this is moving right across the ground, you have, like, let's say your house was kind of like over here, and this is like a summertime where maybe eventually, a storm kind of comes up pretty quick, and then eventually it storms very, very hard, but just for a short amount of time, and then it moves on. So usually after a thunderstorm, when you're in this section now, as it has moved across, you walk outside and you say that it's a little bit cooler. And you're like, well, that's nice, because usually thunderstorms, people talk about that it breaks the heat. It doesn't really break the heat or really even changed it. It just has, the warm air has been pushed back. I should say back and up. So then you have the cold air on the ground. A top-down view that you see mostly on weather maps that you would see, like maybe watching the news. This is the cold front symbol. They look like little icicles kind of coming off the house to me. That's usually how I remember the way that they point is the which way that they're going to go. So cold air is pushing against warm air in this case. And we'll move on to the next one. Warm front. Warm front is very similar to a cold front, except that this time the warm air is going to push against the cold air. The design, though, on the left part of the slide, you can see is much different. It doesn't look like the bullet train kind of going across the ground anymore. The warm air tries to push on the cold air. Cold air is way more dense. It's a lot more difficult for the warm air to push. So it does, but just doesn't do such a good job. It kind of like slants it forward, and it slowly moves it on up. As it does this and slowly moves it forward, it slowly moves the warm air up into the sky. And very similar to our cold front up here, that if you take warm air and you raise it up in elevation, it cools, hits the dew point, condensation, cloud, rain. Warm air moving up at this pace is not going to cause very, very severe storms. It will cause long, drawn-out rainstorms. So it kind of always reminds me, like, if you experience like a nice summer day, and then eventually, the rain kind of comes, and it just doesn't feel like it goes away for like a couple days. That probably is a warm front kind of slowly working over into your area. The map symbol for the warm front is over here on the right side of the slide. It is usually colored red, has these like little half circles. These half circles kind of look like the sun kind of rising up a landscape to me, is what I kind of view it as. So I usually call them like half suns, and they show, and they on the side that the warm front is moving. So in this case, it's moving to the bottom right. So that's why the half suns are on that side. A nice 3D diagram that I definitely did not show in class, but I figured you might like it right now, is these ones. So these are some like old diagrams that they don't work on your Chromebooks anymore. When Flash goes, and about sometime this year, they won't work on anything anymore. But so you're probably one of the last few classes that actually gets to see it. So the idea of this one is the cold front. The cold front kind of comes through, and it just takes that warm air and just pushes it right on up and generates some pretty big storms very, very quickly. That's why the clouds kind of rise so much right there towards the back. And I'll play that for you one more time. So that is a cold front. A warm front, very similar. Warm air comes in and it tries to push that cooler mass of air and kind of slants it as it does so, and then starts making those clouds. But the clouds take longer to form. It just takes a lot longer before you eventually will start kind of getting that amount of rain. And usually that amount of rain is long and extended. I'll play that for you one more time. And that is our warm front. So going back next to the stationary front. So this is kind of the idea that the cold is not pushing enough on the warm to be considered a cold front, and the warm is not really pushing the cold to be considered a warm front. So they push against each other, and kind of nothing happens for a little bit. They just kind of suspend, and as they suspend, though, the same thing is happening often, which is you're getting a whole bunch of air that's rising up in elevation, and like a broken record, if you have a whole bunch of warm air rising on up, it's going to cool, hit the dew point, rain. And so the symbol for that is very, very nicely both of those symbols on the right side. So the warm air is pushing against the cold. That's why you have the half suns right here on the left. And the cold is pushing over here on the warm. That's why you have those blue triangles pushing that way. So it's really the combination of the cold front symbol and the warm front symbol. Based on which way they're pushing. Which one is more dense? The cold. The cold will eventually probably win out as this actually continues. So I'll go back to that 3D model. And then here is a stationary front. So even though the warm air is less dense than the cold, it has some more energy. Maybe it's greater in size at this time for it to be able to kind of push back like a little bit. But in essence, it's still the same thing happens. You still get a whole bunch of rain, and it just stays at location. It stays until eventually one front wins, which is probably going to be the cold, and eventually will push it right on out of your area. But that can take some time, and I will play this one more time. And that is a stationary front. Moving on to our last one, the occluded front. The occluded front is a kind of a special type of front because it is a front where two other fronts really have started to combine. So you have over here the cold air, which is pushing against warm air. So this little section right here is considered to be a warm front because cold is pushing on the warm. At that same time, if you keep on traveling like hundreds of miles this direction, you eventually find out where maybe the warm air happens to be pushing on some other type of air. I call this one cool air. It could be, just as cold as the one before it. Just so you know that this mass is not the same as this mass. But the warm air is pushing on air that is generally colder, and so then this section becomes the warm front. So you have the cold fronts traveling, and then the warm front's over here, and the cold front, though, is faster. Warm fronts since the warm air doesn't really push that well, it does not travel at a greater speed. It travels at a less speed than the cold front. So sooner or later, that cold air over here will eventually travel and catch up to that warm front. At that time, it's going to do the same thing. It's going to take all that warm air in this section and it's going to push it up into the sky, which then causes lower temperatures, dew point, condensation, cloud. And so they all travel in that same direction. So all the symbols in this case would be on the right side. And then they usually combine it. So you'll have like the half circle and the triangle. And then the color scheme can depend. Sometimes they're combined, sometimes they are not. And I'll show you the combined into that purple. And I will show you what that looks like in the 3D model. So you have the cold front advancing from the left side, and then you have the warm front on the right side, and it just eventually catches up. And at that time, then pushes all that warm air up into the sky, which then causes precipitation in rain. So all fronts pretty much have this in common. They're going to cause precipitation. What type depends on the type of front. So more severe is the cold, less severe would be like the warm. And then how they move can be predicted from the type of front they are. So cold will move pretty quickly. Warm fronts will move pretty slowly. Stationary fronts, we see that kind of happening. You know that they're not really going to move at all. So that helps meteorologists determine the weather. And really it comes all down to this, that unstable air and stable air. Unstable air, you have less dense warm air and more dense cold air, and they're side by side. Air is a fluid, and they want to sort themselves out by density. So the warm air has to go up, the cold air has to go down. And eventually when that happens, warm air is on top and cold air is down here, everything is good. They are quite happy. So the occluded front, if you went back, like it will rain for a while, and then it will stop. Because the warm air eventually will kind of have moved up, which is pretty good. And then we continue to go. So our low pressure centers, one thing I should also mention, all fronts are connected to the low pressure center. And a low pressure center is, if you had forgotten, sometimes these words get kind of blended together, is way back at the beginning of the unit. It's these. So it's kind of big L's. So any kind of like map about weather, you will see the fronts always connected to the L's. The low pressure centers, because that's where the air is trying to get to. The opposite of that is the high pressure, which you will not see any fronts connected to because all the air just wants to move away from there. So another reason when you see high pressure, you're like, oh, well, that's going to be pretty good. If you see low pressure centers, then that means fronts, which then eventually is going to mean rain. And then so the next slide is the low pressure cyclones. So we have these storms that are moving across America. They always move from west to east. They circle around those low pressure centers. And then this is what is considered to be like the textbook way that these form across America. It does not have to be like this. When you actually do your lab and kind of activity about this, you probably won't really see one of these exactly formed this way, but it's generally considered to be close. And the whole idea is that you have a whole bunch of cold air working its way down from the poles. You have warm air down here working its way up from the equator. So warm air here pushing against cold air, that will be like a little bit of the warm front. And then cold air here pushing against the warm air down here, so that's a little bit of the cold front. And so they're both pushing. Neither wins currently, so that's called the stationary front. They will continue to push. They're getting to that location where they're meeting. That's probably where our low pressure center has formed. And then they start to move. And pretty much the cold starts to win out. So anything above here, my mouse is kind of circling. Let me get that pointer back. Anything here, this is all cold air. Anything here, this is generally warm air. And this is a low pressure center in the northern hemisphere, so it's circling counterclockwise. And then as time goes on, it kind of stabilizes as this. The low pressure center, and usually the cold front extends south from the low pressure center. The warm front will extend to the east, and it's pushing its way north, while again that cold front's extending south, but pushing its way a little bit to the east. And you can see like the cold front's gaining. So now about 3/4, if you can imagine a circle right here, is cold air, and you just have like that one little bit of warm air pocket left over into here. Moving on, the next kind of stop is here. The occluded front, like this part's starting to meet, where the cold front has kind of caught up a little bit to the warm front, so you're starting to form a little bit of an occluded front over in this section. And then this probably would have caught up more, but usually because of this, the Gulf of Mexico and like the Southern Atlantic has a whole bunch of really warm, wet air, and it kind of re-energizes in essence this little section because that air is pushing up and is pushing to the north, and so that kind of fills that back up. It gives some more energy to kind of like repower this air mass, so the cold front has a hard time kind of collapsing more in onto this, and then it moves the whole lower pressure center up and moves it to over New York. So in New York, our weather generally, not always, but generally our wind direction is to the northeast, so they would call it a southwest wind. That doesn't always have to happen. It depends on where you are technically located in this pressure center, because if you're right here, where my little pointer is, then your wind is actually coming from the west. If you're right here, then your wind's coming from the south. If you're over here, then your wind's coming from the southwest. So it depends on how general you want to make this. The occluded front will grow during this time, and you see my fronts are starting to kind of like shorten because they're starting to weaken. They're pushing more towards the north, which is going to be colder. The warm energy and that air is going to start to decrease. They'll start to get closer together in temperature. This is an actual map of a pretty big storm that happened a long time ago during October. And you see that spiral motion that's going counterclockwise. And this gap right here between these clouds kind of shows like how strong the front really is. To the left and to the right of it, let me move on to the next one. This is those warm front, cold front, and occluded front kind of laid on top of each other. This little section, you can see like that line, it shows you pretty much exactly where that cold front really is pushing onto that warm front. And anything over here is going to be very low in temperature. Anything over here is going to be a little bit higher in temperature until that cold front passes by. But you can start seeing some of the bands. So in general, cold fronts extend south. Now, as you can tell even from this picture, it's not perfectly south. It's kind of like a southwest. And I said warm fronts extend east, and it's not like perfectly east. It's like a southeasty kind of motion. So it's these are very, very general ideas on how these kind of work. The last couple things, and I think we're going to go through it a little bit quicker than maybe normal. But hurricanes, we've talked about hurricanes a little bit in the beginning of the year, in particular. But the hurricane is the same kind of anything and we've talked about this unit. It is a low pressure center, so big L in theory in there, right? And it's going, in this case, northern hemisphere, so it'll be spinning counterclockwise, and it is traveling and energized by warm air that comes from warm ocean temperatures as it goes across the Atlantic. And just based on global wind paths and the prevailing winds, the trade winds by the equator, it pushes them from west to like east to west, coming towards us. And it just so happens that we're located here that they can hit us, and they do. And they move really fast. They have a whole bunch of water that they can dump very, very quickly. If you remember the hurricane that hit Houston a little while ago, that one stalled over that city, and it just continued to rain. It rained about 50 inches. 50 inches is quite high. It's about almost as tall as we are. So you don't really want them to move fast. That's also not including just their wind speed, which is extremely fast too, enough to really damage houses and make projectiles that can fly through the air and hurt people. So that's why we usually evacuate. Our warning system for hurricanes is quite good. We can track them across the Atlantic. We track them all the time. When more are coming, I'll show that to you a little bit later in the year. And so, in theory, they shouldn't hurt as many people as they do. The problem is that usually when a hurricane's coming, people have to evacuate, and they just have to leave to their home, but they usually have to leave their state. Sometimes people have no place to go. So they'll try to ride out the hurricane, which sometimes is possible and sometimes it is not. The other one that is less predictable, but still similar idea, is the tornado. In America, we get practically almost all the tornadoes really for the world is about 80% ish. Tornadoes can happen on every single continent. They can happen all over America. It just is rare for us to find them here in New York. Most of them are found in what's called Tornado Alley. That's more like the Midwest. And that happens because it's very, very flat, as you can kind of tell in this picture. Not really going to see like a whole bunch of mountains or anything like that. And then you have that really cold, dry air coming down from Canada. You have that really warm, moist air coming from the southern Atlantic. So really, really big pressure differences. And really big pressure differences mean fast-moving wind, which then can start a tornado. So a lot of the money and research right now is going for tornado warning systems. Nobody knows if this is going to be real or not, but there is a group that is claiming that they believe that they can do a 1 week warning for a tornado, which is drastically more than like the 5 to sometimes even, or 15 to sometimes even 5 minutes of warning that we actually do get. So that would be definitely a game changer if that actually works out. I'm interested personally to see if that actually is true. And then the last couple of things that we got, El Nino. El Nino. It stands for the Nino, but it really means the Christ child, I believe. I never took Spanish. And pretty much here's how it works. I'll get you a diagram and pull one up for it. Is that if you pull out your reference table and you go to page, I believe 4 or 5, you'll see the global wind currents and the global ocean currents. And the wind at the equator and the ocean currents at the equator move from east to west. Same thing as like that hurricane kind of comes from over here in the eastern part, like kind of near-ish Africa, travels across the Atlantic and then crashes up into North America. Ocean wind currents over here just continue to travel the same direction. As this is going on, it has a neat little side effect, is that you're getting a whole bunch of warm water and it is piling up over here on the western side of the Pacific. And it grows. And it gets bigger, and it gets bigger, and it gets bigger. And there's more and more and more warm water that's piling up here. At the same time, cold water is actually, what they call this upwelling, is upwelling from the deep part of the ocean, going up to the surface, and then working its way and warming up and kind of going back over here to the Pacific. In theory, this is starting like a really nice convection cell down here in the ocean. But water does not really tend to mix very well with different temperatures. And those temperatures are very extreme, then it doesn't really mix very well at all. If we ever get to, I have a nice little lab on that. If we don't, maybe I can take a video of that and show you, or you can probably do it at home if you have different temperatures of water, maybe some food coloring and some salt. But we'll come to that when the time comes. Anyway, so this water is going and it's warming up. And as we know from this entire unit, if you have warm water, you probably have warm air. And warm air is going to be low pressure. Low pressure will rise, and then eventually the air is going to cool, which then will start to condensate when it hits the dew point, and then rain. So that's why they get a whole bunch of rain over here. And that's considered to be like a normal year. But eventually you can get so much warm water here that it starts to fill up, and it gets more and more a part of this ocean. And then what's happening is that you are starting to lose your convection cell, because here it was warm and then cooler. And so that means higher pressure here on the right side and lower pressure over here on the left side. And wind should move from high pressure to low pressure. But when all this starts to fill up, if you kind of remember that isobar lab where you had to draw those lines of like those isolines of pressure, and when they're really close to each other, that means that your wind's going to be very strong. And when they're very, very far apart, that means your wind's going to be pretty weak. If this is starting to become all about the same temperature, then that means then all the air is about the same temperature above, which means then there really isn't any pressure differences, which means those isobar lines become very, very far and spaced apart, which means your winds start to stop blowing. When that happens and the winds start to weaken or drop off, the warm water over here, and that's the bottom part of the picture, moves to the right, and in this case to the east, and starts to go backwards than what it usually does, and it goes all the way back to South America and really starts to make this section of South America warm. So in essence, what has happened is that now you've changed the air pressure, which then changes the winds. And when that happens, now you have a whole bunch of like warm water over here. Warm water creates warm air, low pressure, low pressure rises, it eventually cools, dew points, rains. So anywhere above here in this graphic is kind of trying to show anything above around the Gulf of Mexico in particular, it rains a little bit more. Some of the western states and possibly like northern states will maybe have like a little bit more of a warmer winter than normal. So we see this happen about 6 months in advance. So there's a lot of warning that people know of, like, oh, if it's an El Nino year, it's probably going to be a little bit more of a warmer winter. So like farmers in particular down in the breadbasket of America really use this to see like how much water they're going to get and things like that. And this was figured out a long time ago because cold water upwells, and it actually is quite good for those fish over there. And so this is actually really great fishing time for South America. And those fishermen that lived right across from here. When during an El Nino year, when this all becomes warm water, there's no more upwelling of the cold water, so less nutrients, which means less fish, and the fish will either leave or sometimes they can even die off. So the fishing over here then that time is terrible. So the people who figured out this phenomenon actually were people who went out and fished, which is kind of a neat thing. And then this happens right around December. And so that's where eventually, like December, like Christmas, that's where the idea of like the name, like the Christ child comes from. There's an opposite of this one called the La Nina. That's instead of when you have like the warm waters kind of going backwards, you have extremely cold waters over here. So it enhances the effect. So the pendulum has swung the other way. The last one, just weather forecasting. A lot we could have really talked about before this, but we have some new stuff kind of coming in. There's these things called the GOES satellites, GOES. I believe they're up to new number 17 now. And they are like some really beautiful pieces of equipment that if you have ever looked at some kind of map of storms moving across the ground, usually has some kind of like maybe like a radar on like maybe a weather app. That is where that information comes from. And they can take like such detailed pictures of these storms every few minutes and make those kind of nice moving charts. So the more detailed information we get, in theory, the better we can actually forecast the weather. Doppler radar, been around now for decades, works by pretty much sending out some energy. If that energy eventually hits something in the atmosphere, liquid water, it will be reflected back, and they actually see the shape that it gets reflected back because it gets plotted on a graph. I would love to be able to draw that for you, but pretty much like if you imagine those quad graphs that you do in math, that you have like the quad 1, 2, 3, 4 graphs, they see things that come back, and if they see information of like 0-1 and eventually like maybe like -1-0, so it looks like a flat line. The only kind of water that makes a flat line would be a snowflake. So that's how they kind of get that idea. And if they see something that kind of looks like 1-1 and like there should be like something like over there, or like a -1-1's there, and eventually kind of gets these points that kind of makes it look like a circle. That means like a raindrop. And so that's how they're able to kind of make those radars look, where if it's green, it's raining, and if it's like like a purplishly pinkish, it means it's snowing. That's how they do that. It's mostly math and graphs that come back. So that kind of finishes up. So this is like pretty much like how we definitely weather forecast. We have really good weather data. It's some of the most longest scientific data that we have. It goes back maybe like 150 years or so, mostly because of people's journals, because the first thing that a lot of people write about in their journals is what the weather is that day. And we were actually able to use that to get like what is the weather for a lot of locations. So we use that for our forecasting. So that kind of finishes up our notes. And the thing I have for you guys to do today, besides finish up any kind of past work, and if you have any problems with that, send it to me, this is kind of like our last lab I made for you for our weather unit. It's called synoptic meteorology. Synoptic meteorology means putting it all together. So you will see maps that have, isobars on it. You'll see maps that have the same ones will have weather station models. You'll see the low pressure centers. You'll see the like a cold front and warm front on there. And so that's what people use. And our weather data, we can't just use it just for us. They have to share it with everybody. So the first part of the lab kind of goes back a little bit into time zones. That's why our weather maps are going to be labeled with Zulu time. And so like we can actually actively compare, what is happening over in Europe at one time with some other time and not have to worry about daylight savings times or time zones or anything like that. So we have a good time to go for it. Some of these questions, I believe they're pretty much in there. And they're in the reading. These are the links to actually go to it. That's part A. Part 3 is kind of like, what are some things that are new to you? For a lot of things we talked about the weather is a ginormous topic. It is, people are still studying. They're still trying to figure it out now. Even our best supercomputers are starting to work on still fluid dynamics and how that fluid, in essence, the air moves around in our atmosphere. So there's a whole bunch of new things to learn about. That's that part. This is talking about a little bit more about cold fronts and warm fronts. This talks about pretty much like, how does those cyclones actually kind of move right around. And then it goes into our weather prediction map. And then finally the last part, which is the live weather station data. So the rest of this you can kind of do in pieces if you so desired. This part you need to kind of do all at one time. So you just kind of go to different stations on one of these websites, and I will load one for you now. And this is like what one of those weather maps actually will look like. On the bottom left, you'll see the time stamp, and then you'll see a date stamp. So like over here, that tells you what it times to go. And you can actually move these forward. And this is showing all the weather because I recorded this on the 16th of March. So this is showing like all the weather for pretty much today. And it shows you like the different station models. And then as you might notice, it stops. Like there is no 24 UTC. And the reason for that is because that time has not happened for us yet. So because like UTC is the same thing as like universal time, same thing as Zulu time. So like you would have to wait another hour before eventually you got to see the next one. And the next one actually would show March 17th. So it's because of the different time zones. And they're actually, in England, it's about to go through midnight. So they're almost about on the 17th. So you'll see this thing. So like your data down here, some of your dates will be, probably if you do this on the 17th, some of the dates will be the 17th and some of the dates will be the 16th. But you have to kind of do it because it only shows the past 24 hours. So if you do like half of this, then wait like until tomorrow or the next day, then it's all reset. So it should go pretty quick. Pick a weather station on here, and Albany station might be down, but we can go to high resolution if you want. And like I kind of have to zoom in for some of these. You can do the Albany one if you want. You can actually really do any of these if you want. Just tell me which station model you picked. And maybe the state too, because otherwise it'll be kind of hard to find out some of these. But these are some of the major station models that we have that are all throughout the country. It gives you a small idea of how many we have. Because if you combine these with all like the data from your phones and the data from people's personal weather stations, it's a lot of stuff. Major drawback, just in case you want a little extra, all those station models are down by the ground. That does not really tell us temperature or air pressure or like a lot of movement or amount of humidity in the air above, elevations above. That is the biggest and the hardest drawback of predicting the weather, is that we have really good ground level information. But, how is that different than 500 feet up versus 1,000 versus 2,000 versus a mile? It is a problem. So what we actually do is a lot of these stations will go and they'll take weather balloons and they'll time it. So they all let them go at the same time, and they will do about 2 times a day, and they'll let the weather balloon up into the air that has a temperature and humidity sensor on it, and it will beam back information. If you ever find one of those, you actually can send it back in. They'll give you like a little bit of prize money, which is kind of neat. And but that's how we get our sky level. Now, as you can imagine, like how would that work on a super windy day? about as well as you can imagine. Instead of the balloon going straight up in the air, it goes like practically sideways. So that means that information will be way different. And like in Albany, where the really powerful winds versus like a Rochester, where maybe there wasn't. So there's a lot of issues in just weather collection of really high altitude data. So that becomes a little bit of a problem as well. So that's what I have for you today. So good luck. Have a fun time. If you have any problems, send me an email. And then that's about it. So hopefully you enjoyed this screencast, and they only get better as time goes on, or maybe not. But have a great day anyways.